Hello and welcome to the AICE Chemistry Lecture Series. In this video, we're going to look at Chapter 18, Section 5, which is going to focus on testing for aldehydes and ketones. Something that we haven't really talked about too much, although it has been mentioned in prior chapters and sections, is that a lot of these chemical reactions that we study, especially those that have a visual cue of some kind of observation, can be used for the testing of functional groups. The testing of functional groups is essentially a reaction that will visually tell us, yes, this functional group is present in an unknown solution, but not other functional groups. So it's what we call a selective reaction. So let me write that here. So testing, another form of saying testing is selective reactions. Essentially a reaction that will work and gives a visual cue with one functional group, but not with other functional groups. So some of the tests we have talked about are things like the bromine water or aqueous bromine decolorizing in the presence of alkenes. That's one of the major ones. Also potassium permanganate, turning from purple to clear in the presence of alcohols that can be oxidized, like primary and secondary alcohols. So those are some of the tests that we've seen. But what we're going to focus on today is testing for aldehydes and ketones specifically. And we're going to do this through three different tests that can be chained together. The first test is what we call the 2,4-DNPH test. When an aldehyde or a ketone react with 2,4-DNPH, they create a very unique visual cue in the form of a red precipitate or orange-red precipitate. So, when an aldehyde or ketone reacts with 2,4-dinitrophenylhydrazine, more commonly known as 2,4-DNPH, dinitro, DN, phenylhydrazine, PH. So 2,4-DNPH or 2,4-dinitrophenylhydrazine is a very complex organic compound, and we have it right here. So let me circle that right now. We have this right here. This is our 2,4-dihydrophenylhydrazine or 2,4-DNPH. This big compound will react with the carbonyl group of an aldehyde or a ketone, but not the carbonyl group of carboxylic acids and esters. And we're not going to go into why. The why is a bit complicated. But it reacts in a condensation reaction. So again, this is 2,4-DNPH, and 2,4-DNPH will react with the carbonyl group on an aldehyde or ketone. But again, not with carboxylic acids and not with esters, which makes it a perfect test. Because if the reaction happens, we know that the unknown compound we're testing is an aldehyde or a ketone. When this happens, it undergoes a condensation reaction. Actually, let me use a different color. But when this happens, it undergoes a condensation reaction where the carbonyl carbon is going to be bonded to the nitrogen in the amine group on the 2,4-DNPH, creating this bridge right here, this carbon-nitrogen double bond. In that process, a water molecule is removed from our compound, which is why this is a condensation reaction, because water is eliminated to bond to larger organic compounds. When this happens, this big organic compound that's created between the 2,4-DNPH and the aldehyde or ketone is going to precipitate out as an orange or deep red-orange precipitate. So essentially, because 2,4-DNPH only undergoes this condensation reaction to bind the carbon and the nitrogen, the carbon from the carbonyl on the aldehyde or ketone, and the nitrogen from the amine on the 2,4-DNPH. This only happens to aldehydes and ketones, meaning that this is a perfect test. Because if we add 2,4-DNPH to an unknown sample and we get this deep orange precipitate, then we know that that sample had an aldehyde or a ketone. But if we don't, then we know that sample was some other organic compound. The precipitate that is created, this orange precipitate, can be purified and recrystallized and tested for its melting point. So we can test the melting point of the precipitate to get a much clearer idea of what aldehyde or ketone the unknown originally was. So we can isolate it, dry it, and then test its melting point. We then compare that melting point to reference data, meaning a database with known melting points of this test, of these organic compounds, to identify what that original aldehyde or ketone was. So this is a 2 for the MPH test. It's one of the tests that we can do to identify an aldehyde or a ketone. The problem with this test is that it does not differentiate between the two. When we test an unknown and we get the precipitate, the orange precipitate, we know we have an aldehyde or a ketone, but we don't know which one it is. It could be either or. It could be both an aldehyde and a ketone. So how do we then further eliminate the functional groups to say, okay, this is an aldehyde, or no, this is a ketone? There are 2 tests we can run after a 2 for the MPH test to identify further whether the compound is aldehyde or ketone. And the first of those is a Tollens Silver Mirror Test. Now, if you're in my class, this might look familiar to you because this is actually the reaction that we did earlier in the year during the holiday season to create those holiday ornaments during December, late December. So this right here should look very familiar. We just didn't do it in a test tube. We did it in a globe, in an ornament. So what is a Tollens Silver Mirror Test? Tollens reagent, which is, anytime we say reagent, it's usually a mixture of things. Tollens reagent is a mixture of silver nitrate in excess ammonia. So that Tollens reagent is a mixture of both AgNO3 and NH3, ammonia, in solution, so in aqueous solution. Because that silver ion from the silver nitrate is in a basic environment, and again, a silver nitrate will be AgNO3. Because the silver ion is in a basic solution, it's going to act like an oxidizing agent, and that creates a very mild oxidizing environment, very mild oxidizing agent. When it comes to oxidizing reactions, or oxidation reactions, we know that aldehydes can be oxidized, because they can be oxidized into carboxylic acids, as we saw with the alcohol chapter and earlier in this chapter. But ketones cannot be oxidized. Ketones have no further oxidation, which is also the reason why we don't need to distill them when we're oxidizing alcohols. But because ketones don't further oxidize, silver cannot oxidize a ketone, but it can oxidize an aldehyde. Because of this, when reacted with Tollens reagent, aldehydes will undergo a reaction where the silver ions get reduced into silver solid, creating the visual of a silver mirror. So our observation here, our positive test for the Tollens Silver Mirror Test is, as you would expect, a silver mirror or a silver coating. That's our positive visual, or positive observation. So you can see it right here. When we add Tollens reagent, a mixture of silver nitrate and ammonia, to an aldehyde, we get this silver mirror, the silver depositing, because of the oxidation reaction. Because aldehydes can be oxidized and therefore reduce the silver ions into silver solid. But because ketones cannot be oxidized, if we add Tollens test or Tollens reagent to a ketone, nothing happens. We get just a clear solution with no silver coating. Because of this, we can use a Tollens Silver Mirror Test to distinguish between an aldehyde and a ketone. The aldehydes will get oxidized into carboxylic acid that will very quickly turn to carboxylate ion, and therefore create the silver mirror from the silver ions, creating silver solid as they get reduced, whereas the ketone will just stay clear, stay a clear solution. So this is one test. Now there's dangers to this test, like we mentioned during that experiment during the holiday season. When Tollens reagent gets left to be sitting out for a long time, it can, a long time, I mean a few hours, it can become explosive. And so this is a very cool test, but it does have its dangers of creating some explosive byproducts. So it's not the safest test in the world. A safer alternative to the silver mirror test, which does exactly the same thing, it's just not as cool in my opinion, is the failings test. Failings test does the very same thing that Tollens Silver Mirror Test does, but it does so with copper. Failings test is essentially using copper 2 ions as the oxidizing agent. So whereas Tollens uses silver ions, failings uses copper 2 ions as an oxidizing agent. So a failing solution, very similarly to the Tollens solution, is going to involve, let me highlight it here, failing solution. Let me make this a little big. So the failing solution, very similar to the silver ion solution, Tollens solution, is going to involve an alkaline environment. Only we usually use sodium hydroxide here instead of ammonia. And copper 2 ions. Now, usually in the form of copper sulfate or something along those lines. So we're going to use copper 2 ions with an alkaline solution. And that copper 2 ion can be reduced to copper 1. And then that, because that copper 2 can be reduced into copper 1, the aldehydes can be oxidized into carboxylic acids, whereas the ketones cannot, just like with the Tollens test. So a failing solution will use those copper 2 plus ions to oxidize the aldehyde into a carboxylate ion, because again it's an alkaline solution, and the copper 2 plus will turn into copper 1 plus, which will combine with oxygen from the air and from the solution to create copper 2 oxide and water. Now the oxygen also can come from the hydroxide ions in the solution, that's why this needs to be alkaline, and therefore creating this right here, which is not soluble in water. So when the copper 2 oxide gets created, that is a solid precipitate that gets created. This solid precipitate is orange in color. So let me actually highlight that in orange. That precipitate here is orange in color. And this needs to be a little bigger. Whereas the copper 2 plus ions that it was created from are blue in color. So when we get a positive test for a failings test, when failing solution gets reacted with an aldehyde, the blue solution will convert into an orange precipitate. Now it's very important here that you don't just say that it's an orange solution, because that will be incorrect. It is an orange precipitate. And you need to say that. You need to say it's an orange or an orange solid that gets created from a blue solution. So it goes not just a change in color, but a change in state from a solution to a precipitate. All right. So this is what we see during a failings test. If the failings test is positive, meaning positive. Oh, well, that's an extra I in there. So if the failings test is positive, meaning that we did have an aldehyde in our solution, it will turn into an orange precipitate. Whereas a ketone, or really any other any other organic compound, will give us a negative test, which is going to be a blue solution. And notice it can be very hard to see here, but this is a clear solution. It's blue, but you can see through it. Whereas this orange solution, in the bottom, you can see here, you have a solid there. So it's a solid precipitate, a solid orange precipitate that is floating around in that solution. So it's another way. Again, it does the exact same thing as the Tollens test. It differentiates between an aldehyde and a ketone, just in a different way, in a different observation. Not as cool of an observation, in my opinion. So how can we put all three of these tests together? Well, in reality, these tests need to be chained together, because what happens? If you just run a Tollens test and you get a silver mirror, great, you have an aldehyde. But if you get a negative and you get a clear solution, that could be a ketone or any other organic compound. Same thing with valence test. If you run a valence test and you get an orange precipitate, great, you have an aldehyde. But if you get a negative, that could be a ketone or any other compound out there. So how do we make sure that we are a little more selective? Well, we can run, and if we're on an unknown substance, an unknown sample, we can run the 2,4-D-NPH test. So we can add 2,4-D-NPH to a small amount of this sample, or a sample of this substance. And if we get a negative, if that solution turns clear, then we know it's an organic compound other than aldehydes and ketones. But if we get an orange precipitate out of adding 2,4-D-NPH to a sample of this substance, we know we have an aldehyde or a ketone. We can then do a follow-up test to identify which of those two it is. So then we grab a separate sample, not the one we run this test on, but a separate sample of the substance. And when we run it, we can run an either valence test or a Tollens test. Either or, you choose. If we run a Tollens test and we add that Tollens reagent, the silver nitrate with ammonia, and we get a clear solution, meaning there is no silver mirror, a negative test, then we know we have a ketone in that unknown substance, because we eliminated every other organic compound when it gave us a positive 2,4-D-NPH test. If we get a positive, then we know we have an aldehyde. So if we get a silver mirror out of adding the Tollens reagent, we know we have an aldehyde. Whereas for valence, it's the same thing, right? So if we choose to do a valence test instead, if we add the valence solution, the alkali with the copper 2+ ion, something copper sulfate, and we get a negative result, a blue solution, then we know it was a ketone because we had already eliminated all the other organics. And if it's positive, we get that orange precipitate, then we know we have an aldehyde. So by running the 2,4-D-NPH test first, before we run valence or Tollens, then we can make the valence and Tollens test more definitive, because even a negative test will tell us for sure which functional group we have. So that's how we can use a sequence of testing reactions, or what we call selective reactions, in order to identify specifically the functional group of an organic compound, more specifically in this case, either an aldehyde or a ketone. So that's it for this video. We're going to look at another test in the next section, which is also going to relate to carbonyl compounds. But for now, that's it for today, and I will see you in the next video.